program out of 4 days. We are planning to have 4 days, and today is our first day of the basic applications of design, installation, testing, and commissioning of ACMV HVAC. Stands for air conditioning and mechanical ventilation, or heating, ventilation, and air conditioning, plumbing, fire protection works of construction projects, including, especially today's session is enhancing energy performances in buildings. Ladies and gentlemen, before moving into the whole CPD program, there are certain ground rules which we have to mention here. The chat box, number one, is the chat box is not open for everybody to keep on chatting, and this is open only at the Q&A session, question and answer session. Most probably the core session will not be interrupted by the presenter until he finishes his core session. Most probably somewhere around 9 o'clock, we will finish the core session, and then we open the floor for Q&A sessions from 9 onwards. And the attendance is very important, where you have to have whole 100%, which means the 4 days of attendance to be eligible to receive the certificate. Therefore, attendance marking is very important. How we are doing this marking of attendance is again through a Google form only. Either you can see it from the chat box of the Zoom platform, or else it could be seen in your YouTube live streaming as well in the chat message. To have this access to the YouTube chat message, you have to subscribe the YouTube channel, because we have limited this Zoom platform only up to 1,000 participants, and right now we have more than 800, which means this could reach to 1,000 very soon. Once we have the 1,000 participants, we are not in a position to accept any more participants through Zoom platform. Therefore, we recommend all of you to keep subscribing and keep streaming with the live streaming. You have to keep in touch with the live streaming of the YouTube channel, where we have shared in our WhatsApp groups. And the Q&A session, again, they may not be able to give everybody an opportunity to ask your questions straight away from the presenter. Therefore, what we recommend again, if you have further questions, please type in a WhatsApp message and shoot it to us. Then we will compile them all together and we'll get it responded from the presenter. ඉතාලම කෙටියෙන් කිව්වොත් එහෙම අපි මේ ප්‍රසන්ටේෂන් සීරීස් එක අද පළවෙනි දවස් 4ක් තියෙන ප්‍රසන්ටේෂන් සීරීස් එකේ විශේෂ මතක් කිරීම දෙකක් තියෙන එකක් තමයි අපි chat box එකේ ඕපන් කරන්නේ නැහැ chat කරන්න කාටවත් Q&A session එකකින් ප්‍රශ්න අහන අවස්ථාව වෙනකම්ම ප්‍රධාන දේශනයේ තියෙන වෙලාවේදී අපි ප්‍රධාන දේශකයාට බාධාවක් වුණ ආකාරයට එක හුඟක් දුරට 9ට විතර තමයි අපි ඕපන් කරන්නේ ප්‍රධාන දේශනය අවසන් වුණාට පස්සේ. ඊට අමතරව විශේෂම වැදගත්ම දේ තමයි ඔබේ attendance mark කිරීම. attendance mark කිරීමට chat box එකේ නම සහ තොරතුරු සඳහන් කිරීම අවශ්‍ය වෙන්නේ නැහැ. අපි Google form එකක් මේකද share කරනවා. chat box එකේ සහ YouTube channel එකෙත් අපි chat එකේ Google form එකක් share කරනවා. මේ Google form එක fill කරන්න ඕන දිනපතා. අපි කියන්නේ නැහැ කොයි වෙලේද මේ attendance mark කරන එක අපි දාන්නේ කියලා. අපි ඒක පැය කාලක් වගේ window එකක් ඇතුළත අපි open කරලා තියෙනවා chat box එකේ. සහ YouTube live streaming එකේ. YouTube live streaming එකට සහ ඒකේ තියෙන chat box එකට access කරන්න ඔයාලට YouTube channel එක subscribe කරන්න වෙනවා. එතකොට තමයි අපි chat එක open කරලා දෙන්නේ. Google form එක mark කරන්න. ඔක තමයි ප්‍රධාන කරුණු දෙක. ඊට අමතරව මොන හරි ඔබට ප්‍රශ්න තියෙනවා නම් මේක අපිට සියලුම දේවල් එකපාරට අපිට ඉවර කරගන්න බැරි වෙන ප්‍රශ්න තියෙන දේවල් WhatsApp group වලට එකතු කරන්න. අපි ඒවා විශේෂයෙන්ම ප්‍රොෆෙසර් සහ අපේ ඉදිරියේ ඉන්න දේශකයන් හරහා උත්තර ලබාගෙන අපි WhatsApp group හරහා මේවා share කරගන්නවා. ඒත් එකම අපි තවත් මතක් කිරීම කරන්න කැමති මේක introductory session එකක්. කියන්නේ මේකදී අපිට ගොඩාක් දේවල් cover කරන්න බැරි වෙයි. මේක විශේෂයෙන්ම අපි කතා කරන විශේෂයෙන්ම අනාගතයට අවශ්‍යතාවයන් සඳහා කරන eye open එකක්. යම් කිසි මඟ පෙන්වීමක් පමණක් වෙනවා. මේක පැයකමාරක් දෙකක තුල මේ විෂයන් සියල්ල cover කරන්න බැරි නිසා අපි ඉදිරියේදී තවත් දේශන වලට එකතු කරගෙන සම්බන්ධ කරගන්න බලාපොරොත්තු වෙනවා විශේෂයෙන්ම මේ දේශකයන්. ඒක නිසා අපිත් එක්ක සම්බන්ධලා ඉන්න group හරහා විශේෂයෙන්ම අපි එතකොට updates ටික අපි ඉස්සරහට දෙන්නම්. To start with today's session, we have one of the prominent presenter, ladies and gentlemen, and today's session is all about enhancing energy performances in building. And if I am to introduce the presenter today, let me very quickly go through with his bio. And he's a very famous professor in the industry. Many of who are in the industry know him by the name itself, Professor Athalage, to our names, and by the name he is Professor Rahul Athalage, currently the Dean of Faculty of Graduate Studies and Research of the Sri Lanka Institute of Information Technology. mostly known as SLIT, and a senior professor in mechanical engineering. He was the former Deputy Vice Chancellor of University of Morocco, and he's also an emeritus professor of University of Morocco. He obtained his PhD from Paris in energy engineering, and he's a member of the Institute of Engineers Sri Lanka, member of ASHRAE, corporate member and a past president of Sri Lanka Energy Managers Association, president and fellow Sri Lanka Association of Building Services Engineers, mostly known as LABSI, and member of the Sri Lanka Association of Advanced Sciences, SLAS, and a fellow and council member of National Academy of Sciences, Sri Lanka. The list goes on, and his research areas are building energy systems, industrial energy systems, and solar thermal systems. That's how his bio says, but ladies and gentlemen, on top of everything, Professor Athalagi is an honest gentleman, which he accepted our request to give and share his knowledge, especially with this younger generation and the upcoming generations. Therefore, ladies and gentlemen, please welcome on screen Professor Rahul Athalagi. Sir, it's over to you.
Good evening, everybody. Thank you, Nalin, for that colorful introduction. And hope you can hear me clearly, clear enough, and see my image through the camera. Is it okay?
Yes, sir.
Right.
Everything's good, and please go.
Okay. So let me take it. Let me share the screen. Yeah, hope you can see the screen. That's in. Yeah. You see the screen, that's fine. Yeah.
Yes, yes, please.
Yeah, right. Okay. So, right. I understand that we have time till about 9 o'clock, after which there'll be Q&A session. As Nalin rightly pointed out, this will be an introductory session because the area that is covered under this topic, enhancing energy performance of buildings, is quite vast. But I believe that I have structured in such a way that it will give a stepping stone to many areas, and also engaging to more detailed studies in many areas. So the topic is enhancing energy performance of buildings. So the keyword is energy performance, and the other keyword is the building. So bringing these two together, it becomes a bit of a very vast area to cover. At the outset, I have indicated in red my acknowledgement, mainly to the American Society of Heating, Refrigerating and Air Conditioning Engineers, what is called an ASHRAE. We also have a local chapter. And so information mostly captured by ASHRAE standards. There are many standards. To acknowledge ASHRAE being probably the topmost professional body in this area, heating, refrigerating, and air conditioning. And also, I have captured information from internet sources. So, and therefore, I don't take the ownership of any of these. They have taken information from the internet for the purpose of fair use, that is for education purpose. So with that in mind, let me move into the presentation. The outline very basically is, well, there are about 7-8 points, starting with the energy consumption in buildings. So I forgot one thing to say, that, well, there might be at any moment the power interruption, as you know, that due to the indicated power interruptions in different zones. But if there's a case in a power interruption, I might need 1 or 2 minutes to get back. So please bear with me if there is any power interruption or that nature. So with that, continuing with the outline or the navigation of today's presentation, energy consumption in buildings. Well, the basic background of energy consumption in buildings, then would be followed by how this energy consumption can be optimized through different mechanisms. Firstly, through the minimizing the cooling load. of the, I'll be talking about the cooling load and the difference between cooling load and heating load, and then some aspects related to equipment selection and system design, covering, as Nalini indicated, heating, ventilation, and air conditioning. This includes the mechanical ventilation as well. So we sometimes call it MH or HMVAC, and also some aspects related to building lighting. I have limited only these two, but building services would cover many other areas beyond these. But these two are the main energy consuming, apart from the equipment that are used inside buildings, like and the ancillary equipments like lifts, pumps, motors, and also the office equipment, that kind of thing. Then I will talk very in a mild way on operational strategies, bit on new technologies, and finally standards and labels. And I will capture one or two case studies with simulation results, and also one or two simple examples to wind up the session so that you will have some take-home message and give some thinking to the session that you would be covering today. So with that, let me take this initial slide to do the ice breaking. The energy environmental dimension of buildings. So you see that if you go through the literature, the building accounts for about 30% of the total energy consumption in the world. Global energy consumption, 30% would be consumed by the energy. So that's well known. If you take the segment in Sri Lanka or in Asia, that would be almost the same. So 30% is a huge amount. So therefore, focus attention to conserve whatever possible in terms of energy is important. So when we talk of 30% of energy consumption, you know that most of the energy generation currently still with fossil fuels, except for very small fraction or, well, some non-significant fraction in renewable energy and nuclear. But other than that, it is mainly related to fossil fuels. So obviously, when it becomes power generation related to fossil fuels, obviously unavoidable that carbon dioxide emissions. And carbon dioxide emissions and landfills related to building would also be also a similar percentage. That means about 30%. So talking of a segment or sector, which is the building sector, which is very important in terms of the energy use and in terms of the related emissions that are disturbing the surrounding and local environment and the global climate as a whole. The next important element to note is that the building lasts for decades, especially in local Sri Lankan culture. We don't demolish buildings very easily. It continues over generation over generation. So any decision that you make today in constructing buildings in terms of its energy impact, and that would continue over a long period, because building lasts for a very long period, in particular in our local context, and therefore any inefficiency in energy use or any impact related to emissions will continue over a longer period. So that's important. Therefore, decision making at the design stage is going to be very important. And also you consider, just think the time that you spend inside buildings. So it is estimated that almost during lifetime, that means 90% of our time we spend would be inside buildings, either at our residences or whether at our workplace. It will be mainly inside the building. So building energy consumption, building interior, the climate conditions or the indoor climate is very important, because if we are going to stay inside building 90% of the time, the interior climate condition is going to be very important, not only in energy performance, but also in the consideration of thermal comfort and also the health conditions, right? So I will touch very briefly in the slides that will be coming later. So three aspects I have highlighted: the energy consumption, the thermal comfort or endothermal comfort, and also the health conditions. So these three are very important things when it comes to building. So just we are touching only the energy performance. So you can imagine what other two dimensions can carry. And also lastly, the last point, the indoor pollutants, that is the pollutants inside the building levels have been found after measurements, sometimes 2 to 5 times higher than those found in outside. Because always we say that, okay, it's the outdoor pollution, urban pollution, etc. But we don't pay attention to the indoor pollution. But if you do very precise measurements, detailed measurements, you will find that indoor pollution or pollutant levels are much higher than the most of the time than the outdoor pollution. So therefore, one thing is, well, we spend a lot of time inside buildings. The pollutant levels are much more than what we think, more than the outdoor pollution. So you can imagine how important the building is beyond energy performance of energy efficiency, but mainly related to health. So just to mention that this indoor building, indoor health has become a very important area of study. There are a lot of standards, a lot of attention, a lot of design methods that are coming up. Not much in Sri Lanka, but very soon we will also have to adapt. And therefore, anybody who would be interested in becoming a professional in the building services sector can pay attention to this area as well, in addition to the energy performance, right? Right. Worldwide trend, I've just indicated. There are government initiatives. So since you have the slides, you can go to the details. EU, that is European Union initiatives, G8, that you know that the G8 countries, European Commission, we talk of green buildings, etc. Right. So government level initiatives to look in the perspective of energy efficiency in buildings, right? And the other one is the business community initiatives. Typical ones are the well-known leadership in energy environmental design, lead by the US Green Building Council. That's it's a market instrument, or it's a private entity that certifies buildings as green buildings around the world. Even in Sri Lanka, there are buildings that have been certified by LEED or US Green Building Council. So that is another dimension in buildings beyond energy, going towards more sustainable or green building. Then Energy Star, again, energy efficiency enhancing financing program by private sector. Both of these two are from USA. So why I am indicating is that even though we are in the developing country segment, very soon we will also have this kind of business initiatives or market instruments to improve the energy efficiency. Will bring financing, even though we are now under very difficult financial situation. But this will come because when we are in financial situation, only the improvements in the productivity, efficiency are important. And they are not just merely a grant scheme. They are given to projects to improve energy efficiency and get the benefits and pay back by the benefits that are collected or achieved from the program. So these are two typical examples. Then we also have what are called energy services companies. The Sustainable Energy Authority of Sri Lanka, SLSEA, they have a list of companies who have registered as energy services companies. So they are professional companies who are providing services for when it comes to buildings, building services, and they can carry out energy audit, they can be consultant, they can provide design, they can do the sizing, but all are recognized professional services from the national level. So they are ESCOs. So there are so many other countries have established already. So in Sri Lanka also, this is now getting acceptance. There are also a lot of interest towards green buildings beyond energy efficient buildings. So energy efficient is only one aspect in building. Green building, it goes beyond energy, looking into the other resources of the buildings like water use, water recirculation, indoor air quality, material use, then the surrounding environment, then carbon emissions, like that. So green is again a new area, new in the sense that in today's context, but this has been there for some time. A lot of community, a lot of projects, consultants are in Sri Lanka in operation for these green buildings. So that's an area that you should also pay attention to if you want to, you are envisaging becoming a professional in this building sector area or building sectors area. Clear evidences of transformation that envisages changes in the market practices in the building industry. So we see that the building industry, even despite this all economic and financial difficulties, our construction industry is still continuing. So with the construction in the industry development and the evolution and the growth, you are expected to have all these services supporting this construction industry. That is unavoidable. So therefore, don't have to worry too much. So take this as a challenge and then you have to develop. End-use energy consumption. So this chart would indicate in general. So this is a very standard diagram. Source building energy data book from US Department of Energy. So this is a very important, if you see my pointer, US Department of Energy is, they have a website. It gives access to a lot of information, public domain software in for modeling, simulation in many aspects of building, including the energy aspect of the building, architectural, lighting, and so on. So based on their data, a typical building will have this end-use energy consumption, lighting, heating, ventilation, and air conditioning. So if you drop the H, we will have VAC, ventilation and air conditioning, including that includes mechanical ventilation as well. But when it comes to heating with hot water, steam, etc., or any other heating systems, so then it goes as HVAC. Then office equipment, we have water heating or service water heating. Sometimes you might also have refrigeration in commercial buildings, supermarkets, hospitals, hotels, etc., cooking and other. So in other words, that what we see is lighting, HVAC and office equipment consumes more than reaching about 40% kind of thing, right? So any focus in these areas, understanding lighting techniques, HVAC techniques, and the office equipment or ancillaries would bring benefits because they correspond to a huge chunk of the end-use energy. So input energy is distributed or decomposed into end-use energy in a general sense. So we see that in the next slide, it is a bit more focused to the local context. And more savings can be achieved by implementing efficiency measures around these elements. Obvious, what consumes the most will have to be tackled first. So if we are to see what is to be tackled first, would be HVAC, 32%, according to this pie chart, and the lighting, and then the office equipment. So if you will see that all these devices are covered with some level of standards, meaning that some indication of what to do by the applicants or the end users. High impact measures can significantly reduce energy consumption and cost. Of course, impact, when you talk impact, it is the introduction of technology. It can be existing technology which is well matured, or a new technology that is coming in as emerging technology, but not much tested. That can also be, certain technologies can be captured. For example, this is how the Sri Lankan market captured the LEDs. In no time, in 5 years' time, I think LEDs took the attraction of most of the end users, and now you see that in almost any building, residential to commercial and hotels, they use LEDs. It's a vast development. So therefore, this can be expected. Why I project this is to give you an idea of how end use of energy decomposition takes place. This is more in the Sri Lankan context, covering, I would say, I have not indicated the source, I've just taken from my previous work, covering mainly the commercial building sector in Sri Lanka. So we will have air conditioning and mechanical ventilation, or we say VAC, 50 to 60%. It's a reasonable fraction of the total energy. Electricity, this is from the electricity, and the others that's not falling within the lighting. and ACMV will fall into this category, like ancillary services, the pumping, then the vertical transportation or lifts, what we call, will fall into these categories, inclusive of the equipment of buildings, office equipment. Non-building services related equipment, maybe the process equipment, etc., will fall into this category. Right. Then coming into the energy consumption in buildings. So we have got an idea in these few slides. Well, what are the typical end-use areas of buildings? Why building energy performance is important? The key areas of intervention other than energy, what we have discussed as thermal comfort and in building interior health, are in a composite manner. They are very important. So you really cannot dissociate one from the other, even though our main focus is energy for today in today's context. So you see that typical building, this is very important for BEI, Building Energy Index or indices, or sometimes we call it Energy Use or Energy Utilization Index, EUI. You will see down the line. What are these and why these are important? BEIs are important, energy intensity. For example, depending on the building type, we can define these are the typical building BEIs. For example, if it's a commercial building, you know what the commercial building is. A commercial building, there are commercial activities like supermarkets, slightly different from hotels in our classification from Sri Lanka. Banks, offices, supermarkets, departmental stores, etc. The index is kilowatt hours per meter square for a period, maybe kilowatt hours per meter square per year, kilowatt hours per meter square per month. So usual is kilowatt hours per meter square per year or a month, right? Because it has to be some substantial number. Why meter square? Because total energy would not mean much if you take building A versus building B. If the building A is larger, definitely kilowatt hours per year is going to be large. But if you normalize, what we call it's normalizing, is by dividing by a certain another parameter like area. So then two buildings can be compared because one is larger area, of course, then bringing it or normalizing it to its footprint area will be a good indicator or index for comparison. Or kilowatt hours per person per year. If it's a commercial building, how many people come during the year? How much of energy per person per year? In residential, again, same kilowatt hours per meter square per year or for a month. So to compare, because why it is important, same kind of buildings would generally have same, in general, I use the word general, will have the same kind of activity. Therefore, comparison is important. Office, same. Kilowatt hours per client per year. Hospitals, kilowatt hours per bed or kilowatt hours per patient per year. Hotel, kilowatt hours per guest, or again meter square. Well, any building will generally use the meter square normalization because it's area based. Why it is important? The last sentence. These indices are employed for benchmarking. What do you mean by benchmarking? Benchmarking is to say that when you have a building, let's say you are a consultant in a commercial building, you want to see whether you are doing well or not. Like when you were in school, when you sit for the examination, well, usually you are not supposed to compare yourself with another person. But in Sri Lanka, this happens. So what you do is you make a comparison with, well, how much have you got the average of your year for that particular year in your report card and compare it with another person. So the average marks received by a student can be an indicator to benchmark. So you will compare with another person and say, okay, I have got 88, that person has got 90, so I'm quite close to him. But another person got 50, I am very much ahead. So that's called benchmarking. So these are the typical indicators for benchmarking to say that how well you are doing. If you are doing well, how better you can do compared to the others. And if you are not doing well, what actions you should do to make it much better and fall in line with the others. That's typical in benchmarking. Well, I am not discussing how the benchmarking is to be done. Well, you have large number of data, so there are different techniques for benchmarking. Benchmarking can be done to compare yourself with another company or your building with another building, or benchmarking can be done please remember, in your building with past performance and the current performance. Let's say you make a change in your air conditioning system. You have replaced the old air conditioning system by a new modern new technology with more higher efficiency. So then you can benchmark with your previous performance with the current performance and to see how much energy that you have saved. So benchmarking in twofold: you by present and past, and you with another with similar variety or similar type of activity of the building. So this is very important, even though it looks very simple, but this is an important element in understanding energy performance. Right.
Professor,
yeah,
Professor,
sorry.
yeah, sorry to disturb you, Professor. If you can take about 1 or 2 minutes just to summarize what we have discussed in signals, please.
All right. Okay. So you give me an indication when that is needed. Right.
Yes.
Yes, I'll try my best to give a brief summary in Sinhala. මේ වෙනකම් මම තේරුම් කර දීමට උත්සාහ කරේ ගොඩනැගිලි බිල්ඩින්ග්ස් වල ඉංග්‍රීසි සිංහල වචන පාවිච්චි කරමින් මම උත්සාහ කරනම් භාවිතා කරන බලශක්තිය පිළිබඳ වැදගත්කම ඇයි අපට අවශ්‍ය වන්නේ කියන එක. මූලිකව මම සඳහන් කරා ගොඩනැගිල්ලක් කියන එක අපි ජීවිත කාලයේ 90ක් විතර කාලයක් ඒකෙන් ගොඩනැගිල්ලක් ඇතුළත අපි ගත කරනවා. අපි වාසය කිරීම සහ අපේ වැඩ කටයුතු කිරීම සහ ගොඩනැගිල්ල ඇතුලේ තියෙන අන්තර්ගත පරිසරය බොහෝ වෙලාවට ඒ පරිසරයේ තියෙන පොලියුෂන්, ඒ කියන්නේ අන්තර්ගත රසායනික තත්ත්වය ගොඩනැගිල්ලේ පිටතට තියෙන තත්ත්වයට වඩා දරුණු තත්ත්වයක් තියෙනවා. ඒ කියන්නේ පිටතට තියෙන රසායනික තත්ත්වය නැත්නම් පොලියුෂන් ලෙවල් එක පරිසර තත්ත්වයට වඩා 5 ගුණයක්, 2 ගුණයක් හෝ 5 ගුණයක් පවන ප්‍රමාණයක් නරක තත්ත්වයේ තියෙන්න පුළුවන්. ඒකින්ද අපිට ගොඩනැගිල්ලක තියෙන බලශක්තිය සහ මේ අන්තර්ගත පරිසරය කියන එකට අවධානය යොමු කරන්න ඕනේ. එතකොට මම තව සඳහන් කරා ගොඩනැගිල්ලක භාවිතා කරන බලශක්තිය මොන ආකාරයේද ඒ පාවිච්චි කරන අවසානයේ පාවිච්චි කරන කටයුතු සඳහා, ඒ කියන්නේ වායු සමීකරණය, ඊළඟට ලයිටිං, ආලෝකකරණය සහ අනිකුත් කටයුතු සඳහා මොන ආකාරයෙන්ද බෙදී යන්නේ කියන පයි chart එකක් මම පැහැදිලි කරලා දුන්නා. ඇමරිකාවේ කරපු සංගණනය අනුව 132ක විතර ප්‍රමාණයක් වායු සමීකරණයට පාවිච්චි කරනවා, 125ක ප්‍රමාණයක් ආලෝකකරණයට සහ අනිත් ඒවා 15ක් විතර පාවිච්චි කරනවා උපකරණ. ඒ කියන්නේ 40ක ප්‍රමාණයක් 60කට වඩා වැඩි ප්‍රමාණයක් පාවිච්චි කරන මේ මූලික අවශ්‍යතාවයන් සඳහා. එතකොට ඒ නිසා බලශක්තිය ගොඩනැගිලි වල බලශක්තිය කියන එක කාර්යක්ෂමතාව පාවිච්චි කිරීමටත් නැත්නම් ඉතුරු කිරීමටත් ඉතා වැදගත් වෙනවා. මොකද ඒ අනුසාරයෙන් ඒ ආශ්‍රිතව වයන මුදල් ප්‍රමාණය සහ විශේෂම මුදල් ප්‍රමාණයටත් වඩා ඒ ආශ්‍රිතව ඇති වෙන පරිසරික හානිය. මොකද අපි දන්නවා බලශක්තිය නිෂ්පාදනය කිරීම සඳහා දැනට පාවිච්චි කරන ෆොසිල ඉන්ධන. මේ ෆොසිල ඉන්ධන බලශක්තිය වැඩියෙන් පාවිච්චි කරන ෆොසිල ඉන්ධන එන විමෝචනයත් ඒ සමගාමීව අනුරූපව වැඩි වෙනවා. ඉතින් ඒ හින්දා අපි මේ ගොඩනැගිලි වල මේ පාවිච්චි කරන බලශක්තිය ගැන අපි අවධානය යොමු කරන්න ඕනේ. ඊළඟට අවසාන වශයෙන් කිව්වේ ගොඩනැගිලි වල අපි පාවිච්චි කරන යම්කිසි නිර්ණායකයක් building energy index නැත්නම් BEI කියන එක. ඒ පාවිච්චි කරන නිර්ණායකය වැදගත් වන්නේ අපි ගොඩනැගිලි අතර සංසන්දනයක් කිරීම හෝ අපේම ගොඩනැගිල්ල අපි භාවිත කරන ගොඩනැගිල්ලේ අතීත කාලයේදී අපි පාවිච්චි කරපු බලශක්ති කාර්යක්ෂමතාවය දැන් යම්කිසි වෙනස් කිරීමක් කිරීම තුළින් අලුත් නවීන උපකරණයක් පාවිච්චි කරමින් බලශක්ති කාර්යක්ෂමතාව වැඩි කරලා තියෙනවා නම් ඒ අතීතයේ සහ දැන් බලශක්ති පරිහරණය නැත්නම් භාවිතය සංසන්දනය කිරීමට තමයි මේ පාවිච්චි කරන්නේ මේ නිර්ණායකයන්. ඒකට කියන්නේ building energy index එක. බොහෝ විට ඒක යන්නේ kilowatt hours ඒ building එකේ ගොඩනැගිල්ලේ වර්ග මීටරයකට වර්ග මීටරයෙන් බෙදලා අරගෙන ඒ වර්ග මීටරයකට යන කිලෝවොට් අවර් ප්‍රමාණය හැටියට ගත්තාම ගොඩනැගිලි අතර බලශක්ති භාවිතය සංසන්දනය කිරීමට පහසු වෙනවා. සහ තමන්ගේම තියෙන එක ගොඩනැගිල්ලක අතීතයයි දැනට තියෙන බලශක්ති භාවිතය සංසන්දනය කිරීමට පාවිච්චි වෙනවා. ඒකට අපි පාවිච්චි ඉංග්‍රීසියෙන් පාවිච්චි කරන බෙන්ච්මාර්කින් කියන එක වැදගත් වෙනවා. මොකද ඒක තුලින් තමයි අපිට කරන්න ඕන දේවල් සහ අපි දැනට කරන දේවල් වල තියෙන වැදගත්කම දැනගන්න පුළුවන්. right. මම හිතන්නේ මම ඒ සාරාංශය ලබා දුන්නා. මට මතක් කිරීමක් සිංහලෙන් මම උත්සාහ කරනවා එක්තරා දුරකට පරිවර්තනයක් කරලා දෙන්න. Right. Getting back to this benchmarking, here a typical example. This will give you an idea of what benchmarking is. Now here, in the right-hand side, if you see the pointer, this is taken from the Building and Construction Authority of Singapore. So this is a very important source. They have a lot of information similar to, or not as much as detailed as ASHRAE. It's a 2018. The graph indicates from 2008 to 2017, if I am not mistaken, if you can read, the Building Energy Index, or what we call EUI, Energy Utilization Index, similar to what we had discussed, kilowatt hours per meter squared per year, ranges from some 200 or something going down over the years. But we see that it's a declining trend. It goes. That means energy EUI smaller means that is kilowatt hours per meter squared per year, becoming lower means the building is becoming more efficient. So this is just by following the standards, the buildings that are constructed becoming more and more stringent, following the standards and becoming more efficient. And here you will see that the same thing. This is overall buildings. These are 4 types of buildings, some residential, maybe hotels. And so you will see that each color will correspond to a different building types. All in Singapore from 2008 to 2017, during this 11 years, they have seen that improvements are taking place in terms of the energy utilization index by 11%, 15%, 17%, right? It's quite significant. Just by improving the building performance by following the standards, and also standards would indicate how the replacement and the energy efficient equipment could be done. And the graph in left is important. There are 2 colors used. One is in yellow and the other one is in brown. And this talks of different types of buildings like banks, religious buildings, education, etc. For each of the building, EUI of each building category, because some buildings, depending on its activity, it will have low energy utilization, and some will have last one is the food services, obviously, because a lot of energy is to be used. But what is important is not the type of building, but here the difference between the brown and the yellow. Brown is the current energy utilization index, EUI currently is. For example, this is in US, they are using quite close to about 250 EUI values. And the yellow is they are expecting by their policy to improve the building performance. They expect by 2030, year 2030, this intensity, if it is estimated, it should reach this value. That is about 1/3 of the EUI that is being used now. So that means a huge improvement. So you can imagine 70% reduction in the energy utilization index means less emissions, less power plant needed, more business opportunities and more profits for the organization. So just get an idea of this, and very important in your wherever you work, have a track of the energy utilization index, and there are detailed information to make, to see how these are very precisely calculated. So you can go and to this information subsequently once you finish this stage, right? And let me, yes, right. So that is basically the background of buildings and what in general you should know about how to track the building performance. Right now we'll go to the next level to see, well, why we have to focus on this energy performance. I noted that more than half of energy consumed by buildings is for space cooling. Why space cooling? It's either twofold. One is for comfort of the indoor occupants, like what because we know that the climate is not really favorable all the times. During daytime it is difficult, the nighttime it might be too cold, and the climate changes with season. But irrespective what happens outside, we would like to have a comfortable, consistent environment inside in terms of the temperature, humidity, velocity, and radiation. So that's inside the buildings. You will definitely have to have some conditioning mechanism. So we will call it air conditioning or mechanical ventilation, or condition the air inside, or ventilate mechanically without making changes in the air condition. And to get the best result, we need to optimize. Well, these three are the key important strategies to optimize the air conditioning, or therefore the operation of the air conditioning systems. First is energy consumed by the air conditioning systems or energy performance can be handled or reduced by first minimizing the cooling load. So first strategies, let us see, this can be done at the design stage. Then, so because if you miss that stage, then it's pointless going to the second, optimizing the equipment selection and system design. So once you know the cooling load, to suit that cooling load, you will have to select the system, design the system with properly selecting the different equipment, because air conditioning system is comprised of several subsystems. So each subsystem will have equipment, one or many equipment. So all these will have to be selected and put together to get the design or get the system. So these individual things will have to be very carefully selected to meet the cooling load that was mentioned here. So first step is minimize the cooling load as much as possible. Once you have the minimum, the best cooling load, then you do the proper selection. Well, with the best cooling load, the proper selection of the system design, still it is not adequate if you do not operate and maintain it properly. So we consider that these three are sequentially linked, very important three steps in optimizing the energy consumption. So that, keep this in mind, and I will be talking about these points in subsequent slides, taking each one of them. Right. Air conditioning and mechanical ventilation generally calls for combined effect of three importance. So this slide is very important because this defines the scope of the entire building services air conditioning and mechanical ventilation related scope. First is occupants' thermal comfort. I mean, we have given the first priority for that, because if you are not thermally comfortable, we know that your health will be affected, then your mood will be affected, then your productivity, mindset, everything will be affected if you are not. So imagine in a place where it is too hot or you are not comfortable, you cannot think properly. If you sit for the exam and the exam hall is not properly conditioned for your comfort, then your mind doesn't work, the brain doesn't work, you cannot. So the well accepted standard for this, of course, there are other standards as well. I have mentioned only one because I work with ASHRAE standard 55. So those who are not familiar, you can just see this. You go to the Google and check with ASHRAE standard 55. You should be able to get some information. Of course, to get the standard download, you might have to pay, but you can understand what contained in ASHRAE 55. So ASHRAE 55 understand is by itself is a separate presentation or one or two sessions, right? So the second is indoor air quality. This is, as I said, the health requirement. So now we see that this was not that dominant about 20 years back. Indoor air quality, people are not really bothered. We were just worried only about the tobacco smoke. We said that, okay, no smoking inside. But more than that, there is a lot of things that happen for indoor air quality, because all the buildings, commercial buildings, not much residential, they use different cleaning agents, the detergents, the air fresheners, then the furniture would release certain chemicals, the paints would release certain chemicals, and therefore the chemical composition of the indoor air quality is important. And as we know that we are going to stay inside the building for 90% of the time, that's very important for our health condition, right? And indoor air quality. Right? And the third is, well, now indoor air quality in the modern term, it is extended to indoor environmental quality instead of IAQ, indoor air quality, which is the common and which is handled by the ASHRAE 62.1. Again, you can go to the internet and check ASHRAE 62.1. It will give the brief introduction, the scope, and what it talks about. Now, indoor air quality is extended to indoor environmental quality. It's again a building beyond energy and beyond health. It is related to using daylight, using the aspects of visual comfort, aspect of audio comfort, etc. So beyond the indoor air quality, indoor environmental quality, and mainly on the aspect of being comfortable in your working environment, connecting with the outside, and proper environment inside the building, in addition to the air quality. And the third is the energy performance. That's the performance of equipment and the building itself to provide the best energy efficiency in meeting these two conditions. So therefore, we consider as these three are three corners of a triangle: thermal comfort, health or the indoor air quality, or indoor, it can be even indoor environmental quality, looking from a perspective of audio comfort, visual comfort, outdoor connectivity, etc. And the third is energy performance. So when you want to get better thermal comfort, so if you consider this as three corners in the triangle, when you want to have higher thermal comfort, better comfort, thermal comfort, you might sacrifice indoor air quality and you might sacrifice energy performance. So for quality, you might need more energy and therefore you have to sacrifice. And same with indoor air quality. If you need more indoor air quality, you might have to sacrifice with thermal comfort, or maybe you might have to sacrifice energy performance, right? So these three are related. One cannot be dissociated with the other, so therefore that's important. And the standard that this talks about energy performance is the best, the most comprehensive is the ASHRAE 90.1. Again, you can go to Google and you can find out. And the most recently, high performance building standard integrating renewable energy into the buildings is about ASHRAE 189. All these numbers will have some meaning, and this also updated every 3 years or so. So everything will be followed by a year. For example, ASHRAE standard 62.1 will be 62.1 2007 or 2009, something like that. So overall design intent of a facility should look for all these three in a balance. You cannot isolate each and say, I am interested only in the energy performance. Then you will sacrifice air quality and you will sacrifice thermal comfort. You, on the other hand, you can also not say only I am interested in comfort. Then you will sacrifice this, and you might also may or may not sacrifice the IAQ, right? So that is something that you should keep track of. Minimizing the cooling load, I will accelerate a bit because I have to cover quite a number. So since you have the slides with you, you can always go to this, and you can always contact me if there are any clarifications to me. There are two important terms called heat gain and cooling load. I have given the description. Well, in a building, an important element is what is called the building envelope. So envelope, the basic definition is what is envelope. Envelope is the roof, walls, window, floor or the slab, doors and windows. So it's the shell or the element that separates the building interior from the outside. So whatever happens outside, it's very hot or very cold or snowy or rainy, interior conditions should be able to control irrespective of what happens outside. So that's the basic principle of the building energy systems or building energy performance related or building performance. And therefore, automatically with the building envelope will be the filter that is between building interior and building exterior. So the building envelope material will play an important role, meaning that the roof, walls, windows, doors, and the slab. And the energy exchange between the outside and inside is called the heat gain. That is through the building envelope and to the internal air. And the cooling load is the amount of energy that is to be removed from or to be added in cold climates, to be removed or added, that I'm saying supplied for the indoor occupants. And therefore, the normal thinking why this is well, heat gain should be equal to cooling load, because what is coming into the building should be removed. But it is not true. These two are different. Sometimes heat gain might be larger than cooling load. Sometimes cooling load might be smaller than heat gain, right? The difference comes from the energy storage in the building envelope, because building envelope has certain material that can store energy. Therefore, what comes into the building is, without being added to the air, the building structure will store it, and it will release depending on the situation from time to time. So therefore, essentially heat gain, that is the heat gain by the building, part will be stored or released depending on the time, and only a fraction will go into the interior. So therefore, cooling load is not essentially the same. As I said, it can be larger or smaller, or they are generally it's different. Difference come from the storage. So therefore, building envelope material, its structure plays an important role, because the energy storage will depend entirely on that. And that depending on the building energy storage, your cooling load value will be different. Obviously, if the cooling load value is going to be influenced by the energy storage or building storage, then there would be an impact on the cooling load equipment. So, which decides the minimizing the cooling load is going to be very important in deciding the sizing of the equipment. Hope I can give 1 minute translation, but I have said මම උත්සාහ කරන්න මම දැන් අන්තිමට කියපු ඒවා ටික වම තියන්න මම උත්සාහ කරේ කරුණු තුනක් කිව්වා බලශක්ති භාවිතය ගොඩනැගිල්ල සම්බන්ධව වැදගත් කරුණු තුනක්. එකක් පළවෙනි පියවර තමයි මේ ගොඩනැගිල්ලක් නිර්මාණය කිරීමේදී නිර්මාණ අවස්ථාවේ ඩිසයින් ස්ටේජ් එකේදී බිල්ඩින් එකේ ගොඩනැගිල්ල භාවිත කරන කූලින් ලෝඩ් එක අවම තත්ත්වයෙන් තියන්න උත්සාහ කරන්න ඕනේ. ඒ අවම තත්ත්වයේ තියෙන කූලින් ලෝඩ් එකට සමගාමීව තමයි ඒ කූල් කරන්න යන ඒ කියන්නේ වායු සමනය කරන්න හෝ වායු උෂ්ණත්වය වැඩි කිරීම සීතල ප්‍රදේශවල උදාහරණයක් නුවරඑළිය වගේ තැන්වල අපි මේ හීට් කරන්න ඕනේ. කූල් කරන වෙනුවට ඒ මොන දේ කරන්නත් අපිට අවශ්‍ය වෙනවා යම්කිසි උපකරණ කූලින් or heating equipment ඕන වෙනවා. ඒ equipment වල ධාරිතාව පවතින්නේ අර කූලින් ලෝඩ් එකේ කැපැසිටි එක මත. එතකොට නිර්මාණය කරන අවස්ථාවේ ඩිසයින් ස්ටේජ් එකේදී හරියට කැපැසිටි එක කරේ නැත්නම් හඳුනාගත්තේ නැත්නම් අපි මේ කැපැසිටි එකට ගැලපෙන දාන උපකරණ වල ප්‍රමාණය සායකට යන මිලත් ඒකට බලපානවා. තුන්වෙනුව ඒ කූලින් ලෝඩ් එක හරියට එස්ටිමේට් කළා අවශ්‍ය කරන උපකරණත් හරියට නිර්ණය කරලා ඒ සම්බන්ධ කරගෙන ඒ මිලදී ගැනීම කරලත් ඒක ගොඩනැගිල්ල භාවිත කරන වෙලාවේදී ඒ කියන්නේ ඔපරේෂන් ස්ටේජ් එකේදී හරියට පාවිච්චි කරන්නේ නැත්නම් අර ඔක්කොම ක්‍රියාදාමයේම අසාර්ථක වෙනවා. ඒකින්ද මේ පියවර තුනම අපිට වැදගත් වෙනවා. ඊළඟට මම කිව්වා ගොඩනැගිල්ලක අන්තර්ගතයේ අවශ්‍ය කරන thermal comfort එක නැත්නම් අපිට අපේ ඇතුලේ ඉන්න ගොඩනැගිල්ල භාවිත කරන අයගේ අවශ්‍ය කරන thermal comfort එකට ගැලපෙන ආකාරයට ඇතුලේ condition එක අපි සකස් කරගන්න ඕනේ. ඒ වගේම ඇතුලේ ඉන්න අයගේ සෞඛ්‍යයට ගැලපෙන පරිදි ගොඩනැගිල්ල අන්තර්ගතයේ තියෙන වාතය ඒකේ රසායනික සංයුතිය නැත්නම් ඉන්ඩෝ එයා ක්වොලිටි එක ඒකේ රසායනික වාතයේ රසායනික සංයුතිය තත්ත්වය හරියාකාරව අපිට පාලනය කරගන්න ඕනේ. ඊට අමතරව අපි ඒ දෙක සඳහාම අපිට පාවිච්චි කරනවා බලශක්තිය අවශ්‍ය වෙනවා. ඒතකොට බලශක්තියයි ඉන්ඩෝ එයා ක්වොලිටි එකයි thermal comfort එකයි මේ තුනම නිකන් ත්‍රිකෝණයක තියෙන මේ කෝණ තුන වගේ ත්‍රිකෝණයක තියෙන ශීර්ෂ තුන වගේ කියලා අපිට ඉගෙන ගන්න බෑ. ඒ තුනම එක සමගාමීව බැඳිලා තියෙන්නේ. එකක් අනිකෙන් වෙන්ව ක්‍රියා කරන්න බෑ. ඊළඟට මම කිව්වා බිල්ඩින් එකක තියෙන වැදගත් නිර්ණායක දෙකක් තමයි අපි මේ වායු සමීකරණය කරන සීත කිරීම හෝ කිරීමට පාවිච්චි කරන වායු සමනය කිරීමට පාවිච්චි කරන උපකරණවල heat gain or cooling load කියන නිර්ණායක දෙකක් තියෙනවා. heat gain කියලා කියන්නේ ගොඩනැගිල්ල අපට පරිසරයට සමග සම්බන්ධ වෙනකොට ගොඩනැගිල්ලට ලබා දෙන තාප ප්‍රමාණය ගොඩනැගිල්ල තුලට ගොඩනැගිල්ලෙන් පිටකට සහ කූලින් ලෝඩ් කියලා කියන්නේ ගොඩනැගිල්ල අන්තර්ගතයේ තියෙන අන්තර්ගත වෙලා තියෙන වායුවේ උෂ්ණත්වය අනිකුත් තත්ත්වයන් ආර්ද්‍රතාවය වැනි තත්ත්වයන් යම්කිසි නියත මට්ටමක තබා ගැනීම සඳහා කොයිතරම් බලශක්තිය කියන්නේ කොයිතරම් තාප ප්‍රමාණයක් අපිට එළියට යවන්න ඕනේද ඇතුළට ගන්න ඕනේද කියන එක තීරණය කිරීම. මේ දෙක හීට් ගේන් එකයි කූලින් ලෝඩ් කියන එකයි දෙක සමාන වෙන්නේ අපිට බැලුවාම හිතනවා මේ දෙක සමාන වෙන්න ඕනේ ඇතුළේ තියෙන හීට් එක කූලින් එකෙන් අරන් දාන්න ඕනේ කියන එක. එහෙම වෙන්නේ නැහැ මොකද ගොඩනැගිල්ලේ තියෙන එක්තරා දුරකට තාප ධාරිතාවක් තියෙනවා. ඒ ධාරිතාව තමයි තීරණය කරන්නේ මේ දෙක කොච්චර දුරට වෙනස්ද කියන එක. අනිවාර්යයෙන්ම මේ දෙක වෙනස් එකක් අනිකට වඩා ලොකුයි කියලා අපිට කියන්න විශාලයි කියලා කියන්න බෑ. සමහර අවස්ථාවේදී ගොඩනැගිල්ල ස්ටෝරේජ් එක අනුව හීට් ගේන් එකට වඩා වැඩි වෙන්න පුළුවන් කූලින් ලෝඩ් එකට. මොකද ගොඩනැගිල්ල සමහර වෙලාවෙදී ගොඩනැගිල්ල ස්ටෝර් කරගෙන තියෙන එක ඒ වෙලාවේදී ඒ මොහොතේදී පිට කරන ගොඩනැගිල්ල ස්ටෝර් කරලා කියන ගබඩා කරලා තියෙන එක පිට කරන හින්දා එළියෙන් එන එකටත් වඩා වැඩිපුර ප්‍රමාණයක් කූලින් ලෝඩ් එකට භාවිතා වෙන්න ඉඩ තියෙනවා. ඒකට ඒකින්ද ඒ දෙක තීරණය කිරීම සිදුවන්නේ මේ ගොඩනැගිල්ලේ ගබඩා වෙලා තියෙන තාප ශක්තිය අනුවයි. ඒක තීරණය වෙන්නේ ගොඩනැගිලි මැටීරියල් එක ඒවයි ප්‍රමාණය ඝනකම යනාදී ඒවයි තාපධාරිතාවන් මත. ඒ ටික තමයි මම සඳහන් කරේ. මම ඊළඟට උත්සාහ කරන්නම් මේක සාමාන්‍යයෙන් සමස්තයක් ඇටියට අපි A level පන්තිත් ටිකක් භෞතික විද්‍යාවට පාවිච්චි කරන දේවල් වගේ තමයි මෙතන තියෙන්නේ. Cooling load එක දැන් අපි කතා වුණා cooling load එක minimize කරන්න. So we talked about minimizing the cooling load. So what are the elements that I said the building envelope is the one that is responsible to interact with the surrounding as a function of the interior condition. So first element is the conduction through the walls. The building as a roof, the walls, the glazing are the windows and might be the doors and the slab. So the first element is the conduction, that is heat interaction between the outside and inside through walls, glazing and the roof through conduction. The second is again through windows and opening, the ventilation. The air will move from inside to outside or outside to inside or air exchange. That's called ventilation. Maybe voluntary or involuntary. Sometimes it's involuntary because that's called infiltration. We expect everything to be closed, airtight, but that's not so. So then air exchange will take place. But if it is, so then we call it infiltration, not exactly ventilation. Ventilation is the air that is required deliberately, purposefully brought into the building. It's mainly to control the air quality inside the building with the health requirement. Then the third is the solar radiation. That's first two are related to the surrounding, immediate surrounding, outside conditions, temperature and the air movement. The third is coming from the sun and which enters the building through the glazing, that is transparent part of the walls or the windows. And the last one is the internal heat generation. Then generation of the heat inside the building due to people, because each one of us, based on what we have taken as food, will get converted into energy and that will be released into the building. And the energy supplied to the equipment through the operations, all this will get added into the building interior. So the internal heat generator. These are the four elements. Conduction. So this will depend on the material of the wall and the windows. This will depend on the size of the opening. This will depend on the material properties of the window, the transparent material. And this will depend on the efficiencies of the equipment and the number of people. So each one of us, well, depending on our activity, would release at least 100 to 120, 150 watts. If it's a gymnasium, etc., maybe even more than that. So that energy, imagine if you have 10 people, so you have 1 kilowatt inside the building. It's like burning a 1 kilowatt lamp. And this interaction to total cooling load is generally divided into two: sensible cooling load and the latent cooling load. Right? So sensible cooling load talks of only by a change of temperature. Latent cooling load is only based on, don't talk of the temperature, but the given temperature is based only on the moisture level, that is adding or removing moisture into the interior of the building. So these are the 4 elements. And this is the standard for minimizing the cooling load. The standard that deals with is the first standard is ASHRAE standard 55, which talks of the thermal comfort. And well, thermal comfort can be under air condition using mechanical cooling, or it can be comfort related to the ventilation, but without using a mechanical device. So these 2 diagrams represent, this is the standard. I think you might be, some of you at least might be familiar with the psychrometric chart, where the standard says for a standard activity, that's normal activity, what is measured in MET, that is the activity that converts the energy that you have in your food into heat. Then the clothing level, this is the clothing resistance, velocity inside the building, and the radiation of the surfaces around you, that's the wall, the windows, etc. The combination of these will decide, well, the interior conditions, and this will, based on the interior condition, this will give a certain sensation of comfort, which is given a number called the predictive mean work. So this hatched zone is the zone for under summer conditions. The other one is for winter conditions. Let's say we forget the winter condition. This is the summer condition. These are the combination of temperature and humidity where you will feel comfortable, or this vote for this is between -0.5 and +0.5. And the standard 55 will indicate how you can well get this vote of people within this band. And this has been established by a large number of tests carried out by ASHRAE. And the target of the cooling load starting point would be your interior conditions should fall within this. And if it is ventilated building, your interior conditions should fall, it's on your temperature, would fall based on the outdoor temperature within this zone. So the standard will indicate how your interior condition should be decided. And based on the interior condition, you will have to decide on what the cooling load is. For the cooling load, the starting point would be the internal temperature and the humidity that you are going to make use of. And that's why standard 55 is important in deciding the cooling load. Right. So, මෙතන උත්සාහ කරන්නේ එකපාරම කියලා ඉවර කරන්නම්. Cooling load එක තීරණය කර ගැනීම සඳහා අවශ්‍ය කරන තබා ගැනීමට බලාපොරොත්තු වෙන උෂ්ණත්වය ආර්ද්‍රතාවය මේ zone එකේ මේ කොටුවෙන් පෙන්නනවා. ඒ කොටුව ඇතුළට අවශ්‍ය කරන මේ තියෙන ඕනම තැනක තියෙන උෂ්ණත්වය ආර්ද්‍රතාවය ලබා ගැනීමට අවශ්‍ය කරන උපකරණේ ධාරිතාව තමයි cooling load එක හැටියට පාවිච්චි කරන්නේ. cooling load එක තීරණය කර ගැනීමට ප්‍රථමයෙන් අපි තීරණය කරන්න ඕනේ ගොඩනැගිල්ලේ ඇතුළත අපි පාවිච්චි කරන උෂ්ණත්වය ආර්ද්‍රතාවය මොකක්ද කියන එක. මේ රූපය පාවිච්චි කරන මේ ඩයග්‍රෑමේ පාවිච්චි කරන්නේ අපි mechanical cooling උපකරණය පාවිච්චි කරනවා. මේ ඩයග්‍රෑමේ පාවිච්චි කරන්නේ thermal comfort එක සඳහා ventilation, ඒ කියන්නේ cooling උපකරණයක් නැතුව එළියෙන් තියෙන හුලං අපිට openings වලින් windows doors වලින් ඇතුළට ගත්තාම මෙන්න මේ condition එක, මේ උෂ්ණත්ව condition එක ලබා ගන්න පුළුවන් නම් අපිට ඇතුළේ thermal comfort එක ලබා ගන්න පුළුවන්. ඒකට ඒ කියන්නේ mechanical cooling නැතුව thermal comfort එක සහ මෙතන mechanical cooling or heating සම්බන්ධීකරණය කරන comfort එක තමයි ඒ දෙකෙන් දැන් පේන්නේ. ඒකට සම්බන්ධ තාක්ෂණික උපකරණ සිලෙක්ට් කිරීම සඳහා තෝරා ගැනීම සඳහා පාවිච්චි කරන තාක්ෂණික නම් ටිකක් තමයි තියෙන්නේ. These are the terminology used in selecting the cooling equipment. I will not go into the detail of that. You will have this information. Therefore, the cooling load can be minimized by, as we have discussed, heat exchange between the building and outside, solar heat gain through the openings, and the storage effect. And for energy efficiency, due attention should be paid from the design stage of the building. So these are the things that we can control from the very beginning. The aspects related to the heat between the outside and inside the conduction. This is through the radiation, and this is through the storage effect. Yeah. So the basic elements are the orientation of the building. So we are talking of the building envelope, how the building envelope have to be oriented. Depending on the orientation. Orientation means the angle of the building with reference to the geographic north or the magnetic north-south. That will have an impact on the energy performance. Why? Because the building orientation will be relative to the movement of the sun, and therefore that will decide how much energy that it will capture, the building will capture, and how much energy will penetrate into the building through the openings. So therefore the orientation is important. Then the material property of the envelope. Why material properties are important? Because we discussed that the cooling load is affected by the storage. So material properties will decide. So if it's brick, there will be one kind of storage. If it's concrete block, that will be another kind. If it's in wood, yeah, something. If it's in structure, this steel structure with some other material mixed with, let's say, the bricks or anything, then another storage level. So therefore, building envelope material will have an impact on that. Provision of shading. So if there are, the building envelope can be shaded from outside, can be shaded if these windows, they can be shaded. And the other one is reduction of air into the building or from the building to the outside. That's unintentional. That's why it's called air infiltration. And all this will reduce the cooling load beyond what we expect. So this I have explained why the orientation is affected. Then I have also indicated why material properties of the building are going to be important. Two other important things are when it comes to the roof, the roof and the outside building wall colors. If they are used bright colors, the absorption of the solar radiation will be very high. Therefore, it is always better to have in climate of like the tropical climate like us, to have light colors so that the radiation falling onto the building walls and the roofs can be reflected back. Therefore, less heat exchange will take place from the outside to inside. The standards will say that solar reflectance, that is, this is 79% of the radiation should be reflected. The materials used should be of this order. And WWR is the window to wall ratio. Windows should not be very large. Window area divided by the wall area should be less than 40%. So that's why. These are two important elements that are given in the standards. Shading devices. Well, shading devices can be to protect radiation falling onto the walls. Then also it can protect radiation going through the windows. And they can be external shading, for example, like trees or any cladding or any other external stuff, or it can be internal shading such as curtains or blinds, or it can be shading incorporated into the glazing or the glass material like tinted. Then we can also have reflective glazing. That's material that are pasted onto the glass. And we also have low emissivity glass. It's another improved version of material of glass. That means it will absorb energy, but it will release energy back into the building by a very low amount. And the other category is called the selective glazing. Selective glazing is that it will permit visual light transmission, but not the heat component, because we know that from radiation coming from the sun, it will have both components, light, the component corresponding to the light, that is for visual action, and corresponding to the heat that is coming from the sun. And therefore, the glass, certain glasses can separate these two and allow only the light, not the heat. So it's a bit expensive, but that's still possible. And the other one is weather stripping or caulking, that is to ensure that no air leakage will come into the building, and also to employ revolving doors that you have seen in hotels and so on to reduce the air infiltration. So these are the shading devices, glazing or the glass, or then shading. This is on the glass material. This is in addition to the glass material from outside or inside. And this is working on the, again, glass material, talking on the heat component of the solar radiation. And the standards will say if it's a single glazing, what is the conductance value? If it's double glazing, it's what's the value? And when you decide on these values, that will have the impact on the cooling load. And so that's called the U value. Solar heat gain coefficient is the how much heat is absorbed and then again in return sent back into the building. So the shading coefficient is the fraction of shading that is given by the glass depending on the transmittance value. And overall thermal transfer value is the overall value given to the composite value, incorporating walls, windows, and so this value can be computed, and the standards will give how this can be calculated. And ideal, it should be in the range very close to 50 or so, but currently Sri Lanka uses values close to 90. So these values are obtained from the standards, and this diagram will indicate how the radiation coming from the sun is separated into different components by a glass. And so you will see that here you will have visible light that is coming from the sun. One fraction is corresponding to the action of seeing. The other one is the heat one. And the glass, if it is with proper characteristic that we desire, it will allow only the visible part, but not the heat part. Heat part should be reflected back. So the actions that I indicated by having a tinted glass, low emissivity glass or selective glass would be to make sure that only visible light will come into the building and the others will. But normal glass will allow both visible light and the heat or infrared to come into the building. Therefore, the cooling load will be affected. And this is a table that you will see that I have captured from the ASHRAE 90.1. ASHRAE 90.1 is the ASHRAE standard for the energy performance. So depending on where the building type is, non-residential, residential, or heated building, and depending on the element of the building envelope, roof, walls, walls below the roof, the underground, then floors, slabs, etc. It will indicate what is the value of the conductivity, that is this value, this U value, how this value should be maintained in each of these building envelope element. So at the design stage, for each element, you have to check whether your design is going to be capturing or meeting this requirement so that the cooling load is minimum, right? So I have just taken only a caption, and if you go to the ASHRAE standard, you will find this, right? So all what I have discussed was to see how cooling load can be minimum. So මේ අන්තිමට කරපු ස්ලයිඩ්ස් ටිකේදී මම පාවිච්චි කරේ cooling load එක අවම කර ගැනීම සඳහා building envelope එකේ පාවිච්චි කරන भित्ति walls, roofs, windows වල මේකුත් නිර්ණායකයන්, ඒ කියන්නේ තාප හුවමාරුව තාප අවශෝෂණය අවම වෙන පරිදි පාවිච්චි කරන්න භාවිතා කරන්න ඕන නිර්ණායකයන් තෝරා ගැනීම සඳහා ASHRAE 90.1 කියන ස්ටෑන්ඩඩ් එකේ තියෙන දත්තයන් කොහොමද යොදාගන්නේ කියලා. ඒ දත්තයන් මේ ස්ටෑන්ඩඩ් එකේ කියන ආකාරයට මේ බිල්ඩින් කැටගරි එකට non residential, residential සහ heated buildings හැටියට මේ තියෙන values පාවිච්චි කරුවොත් භාවිතා කිරීම තුලින් අපිට cooling load එක minimize කර ගැනීමේ හැකියාවක් ලැබෙනවා. ඊළඟ කොටසට අපි සම්බන්ධ වෙනවා නම් equipment selection වල equipment selection එකකදී අපිට වැදගත් වෙන කරුණ තමයි අපි equipment එක ඒක ගොඩනැගිල්ලකට සම්බන්ධ කෙරුවාම අපි හැම වෙලාවකම අපිට සාමාන්‍යයෙන් දකින්න දෙයක් තමයි ඒ භාවිතා කරන කැපැසිටි ධාරිතාව උපරිම ධාරිතාව පාවිච්චි කරන්නේ ඉතාමත් කලාතුරකින් තමයි. මේකේ AC system works at full load only at a fraction of the total running hours, 20 to 30%. Therefore, considerable amount would run on the part load. That is, if you take an equipment now, cooling load, we have to select the equipment to match the cooling load. So we know what is the difference between the heat load and heat load and the cooling load, or the heating load, heat gain and the cooling load. And the cooling load, well, once we fix an equipment to a particular load, we see that very rarely it will run at the full load condition. Most of the time, 70 to 80% of the time, it will be outside the full load condition. So therefore, equipment will always operate at the part load condition. This is a very important thing. All mechanical equipment, that is chillers, boilers, compressors, even automobiles, that's internal combustion engine, will operate efficiently, not at the full load, but at part load. Most of the air conditioning devices will be more efficient between 60 to 80% somewhere there than the 100% load. So when we size an equipment, if you have a equipment slightly oversized and expect the building to operate in the 60 to 80% of that equipment sizing, then we can expect the equipment to operate at a higher efficiency than working on the full load. So that means that if you just try to meet the capacity to just meet the requirement, not slightly allowing and leverage of load slightly above the requirement, it will not be in a zone of 60 to 80%. Let's say 60 to 80% is arbitrary, but in that range, it will depend on what the type of equipment is that. So in addition, we also have 5 to 10% margin kept for calculation. So in general, not much of an issue trying to slightly oversize, so that in actual operation, it will operate not in the full load, in the part load condition. So one might think that why do you need to oversize? Because you might be spending unnecessary initial investment. True enough. Why slightly oversizing, you pay additional investment for the initially. But since it's operate efficiently and the operational period is quite longer than and the operational cost is quite higher than the initial cost, it's better and more not a bad idea to get the part load performance and allow the equipment to operate at a better efficiency. So all this will apply when you come to the equipment selection. These are the types. You will have the one segment, unitary systems, small units. Then you have something in between, what we call the package or the factory fitted units. And you have the central systems that's either based on water or refrigerant cooling air and air circulation, or entirely based on a water cooled system, or water chilled and circulated through the building. Mainly, then heat rejection can take place. So that's the first category. We also have, depending on the heat rejection based on air cooling or water cooling. So always water cooled heat rejection is much better than air cooling. Then when it comes to the air supply, we also have constant supply of air, what we call constant air volume, or variable supply of air, where air flow rate can be varied depending on the load condition, and we call, so this appears to be more efficient than that, but the cost will be higher. And we also have a new variant, or not really new, some time back, but subsequent evolution, what we call the variable refrigerant volume. So instead of having the prime mover or the compressor changing according to the load, We also, in addition, and can be in addition, they're trying to very precisely control the refrigerant flow to meet the load requirement, which is efficient operation, and it's well, recent development compared to the other variations. Equipment, large buildings will have, so we saw the equipment category, unitary, the small systems, window split units. So not much of variation, and also their efficiencies are poor. And when it comes to large equipment, well, larger equipment, you have more leverage to have higher equipment efficiencies and accommodate in larger systems. Large buildings use central chill water systems because, well, it can be in one particular place. Maintenance would be easy, distribution, and it is more efficient. Depends on how the operation is. So because it will be central, and distribution can be very well controlled and efficiently managed. But sometimes you might have in a building, its operation might be not very consistent. You do not know how it is going to be in operation. But in that context, still a central system can be used. Or you need more individual level manipulations and monitoring, or if not, have a completely individual small systems where units can be operated depending on the end user's discretion. Even though it may not be efficient, but it might suit the operating requirements of the end user. The large building with a central system, which will have components, the heart of the cooling system is the chiller, which will produce the cold water. So cold water will carry the coldness to the end use level, or it will transfer into air, and air will carry the coldness into the end use. That's possible. That's all air systems. Then you will need pumps or motors, pumps and motors to circulate the water and drive the pump with motors. We'll have cooling towers to cool the condenser or heat rejection, and air handling units to carry the coldness from the either chiller directly on through a secondary circuit. So this is a typical central system. You have two. Well, generally you have different design strategies. So this is all will come under the design, equipment selection, and system design. Central systems will have either air cooled or water cooled. So here in this case, we have the cooling tower. That's heat rejected from this through this condenser. Water pumps will take it to the cooling tower, cool back, and then brought back again to the chiller. And the chillers will have its normal cycle. The refrigerant cycle will have a primary circuit, and will through pumps, the chill water will be circulated, and then through a secondary circuit, chill water will be taken to the building end use condition. So this is a very generic schematic diagram. Well, it is quite customary, normal to have multiple chillers. One is to be able to do the loading depending on the load requirement, one, and then go to the next. And usual is that we call to have redundancy. That is, if there is any requirement for maintenance or that kind of thing, we always have additional chiller. That's the normal practice, what we call the N+1. One unit in addition. So you can change over to that unit, and then you can attend to that maintenance work. But it is also possible to have run all at part load. If we know exactly the best operating point, the combination of part load can take place. And that's also possible. That's quite common in cooling towers. Instead of running several cooling or one or two cooling towers, you run all the cooling towers, but all running at part load, trying to get the maximum advantage of the equipment part load conditions. This is a typical air distribution of inside. And as I said, cold water can be coldness can be transferred to the circulating air, and the air can be distributed to different zones. For example, like this. So we have a single duct catering multiple zones, but it will be a constant air volume system. So this configuration will indicate the air will be supplied at a constant volume. But if the load is higher, then at this point, you need the lower temperature. When the load is lower, you need higher temperature. So constant air volume will ensure that the air volume rate is constant, but the supply temperature will have to be varied. So therefore, your cooling coil will have to be adjusted to suit the lower requirement. And in contrast to that, we also have the same thing with variable air volume. The same example where the temperature would remain the same, but the quantity of air, the cold air supply, so the temperature would remain the same, 55 Fahrenheit. But here the load is high because it's internal load is higher than this. So you need a lower flow rate here because the same for the temperature. And here you need a higher flow rate for the higher load. So here, because of that, true enough that you have to reduce the flow by choking or damping the flow rate, which will cause some energy loss. But however, here you maintain a constant temperature. Therefore, overall energy performance is much better in this variable air volume configuration compared to the constant air volume configuration. And as I indicated, we also have the variable refrigerant volume, VRV, so which will go into from a central point. Refrigerant supply will be different depending on electronically controlled, depending on the load condition. It can have, so quite a lot of flexibility is available, and also electronic controlling of the thermostat condition, and electronics taking the signal to the compressor is also needed in this configuration. Equipment selection. Chillers consume the larger component of AC, and water-cooled chillers are efficient than air-cooled because of the better heat transfer condition. 10% increase in chiller efficiency brings 3 to 4% reduction in the building energy consumption. That's a very importantly. 10% increase in chiller efficiency. That is, if you increase the chiller efficiency by 10%, you can reduce the overall energy consumption 3 to 4 based on experience. Typically, highest efficiency is demonstrated between 60 to 80% of the capacity. This I have discussed. Any mechanical equipment will have a part load efficiency much better than the full load. So, and the efficiency values are really indicated by coefficient of performance. These are the typical values, typical indicators. Energy efficiency ratio, or EER, or another indicator is kilowatt per ton of refrigeration. So this is for the chiller. Or the entire system, we can have kilowatt per ton of refrigeration. This kilowatt would be all the electricity, the power consumption of inclusive of chiller, water pump, pump circulation, energy power for the chill water, condenser water, and fans, etc. So this is the typical. These are the typical indicators normally used. Earlier time, COP was very dominant. Now it is more kilowatt per ton of refrigeration. That is kilowatt of electricity use per unit of cooling. So this gives a good indicator of how efficient either the chiller or the entire system. Typical values, now we reach kilowatt per ton of refrigeration, maybe 0.38, 0.4, and system kilowatt per ton might be about 0.8 because of the inclusion of the pumps, fans, etc. All the distance will have to be taken by proper understanding of the cooling load of the building. Cooling load, this is something that can be measured or can be obtained by simulation. You see that early mornings load and it goes up. So therefore, depending on the load requirement, we can decide on the number of chillers. So here you can have a smaller chiller, then you can have an additional one, and at the top you can have, so depending on your end use requirement, you can decide on number. So you can also put one single chiller to cover everything. So then here that chiller will be at very very low load condition where efficiency will be quite poor. So equipment selection and the number of chillers would entirely depend on the cooling load profile, which have to be properly estimated. And this is a diagram that will indicate, which I said, part load performance. So here it's the efficiency kilowatt per ton as a function of the percentage of load. You see different chillers, reciprocating chiller, screw chiller, centrifugal chiller. You will see that the efficiencies are this kilowatt per ton. The number, lower the number, better the energy consumption, energy performance. So here you will see that, except here, where the lowest efficiency is about, this is centrifugal chiller, about 45%. But here, screw chillers, small chillers will have 60 to 70% the lowest kilowatt per ton. So therefore, you will see that 100% load efficiencies are not that better than the 70% efficiency. So you can, by slightly oversizing, you can operate in this region. So that's where the equipment selection is important. And if you want to estimate the actual energy consumption, the manufacturers provide the number called integrated part load value. Integrated part load value is estimated based on the A, B, C, D value given by the manufacturer. And based on this, you can compare two systems or two air conditioning systems or equipment based on what is the best IPLV value rather than the overall full load efficiency. But this is a combination of 100%, 75%, 50%, 25% load. So which will give a better picture in the actual operation. And this is based on the ARI standard working conditions on a particular condensing temperature, particular condensing flow rate, and particular evaporator temperature. In addition, an equivalent of this is called non-standard part load, where equipment is located in a under condition which is not given in ARI, but that this number can also be estimated based on the manufacturer's information. This will indicate for different types of chillers, small electric chillers, large electric chillers, air-cooled, water-cooled. What's the COP value? So you see that water-cooled chillers have a higher COP value than the air-cooled chillers. And larger chillers will have a better efficiency or COP than the smaller chillers. This is something that I have indicated. This is for a special case where chillers are driven by engine. And this is another different type of air conditioning system. It's called absorption air conditioning, which is different from the electric vapor compression based air conditioning. We have a problem with the time. Chiller, consider providing the building cooling load by multiple chillers. So we saw that looking at the type of the building. So building load is not a constant. If building load is constant, one chiller could handle the thing. But if it is not constant, if it's only a peak at a certain time, very small fraction, so then it's always better to have a segment, a smaller chiller to handle the smaller load, medium chiller to medium load, and to capture the higher load, so higher chiller. So they have to be sequenced in a proper way. Everything depends on the finances. And make use of the part load efficiency kilowatt per ton. And here there's an example carried out by estimations for you to get an idea. Example, 1,000 tons peak cooling load can be. So, for example, in this diagram, assume that this is 1,000 tons. Yeah, here it's 1,800. For example, it's a yeah, so for that example, 1,800 ton, you can have different configurations with a combination of 1,000 ton chillers and 500 ton chillers, right? And down the line, we will have, I will show you some results, how the combination to be taken up. And here in under equipment, all the central chillers will have some level of fan or a pump, and this will indicate how fan or a pump should be properly used, because the flow rate will have to be varied, and therefore pumps and motors have to be selected accordingly, mainly to consider the variable flow conditions. Just noting that pumping power is proportional to the power, the flow to the power 3. So that is a slight variation in flow can affect the pumping power. So this is by laws of fluid mechanics, and therefore pumping will be affected by the variation of flow conditions, and this can be taken as an advantage. Try to avoid oversized pumping. So if you have oversized pumping, it will cause unnecessary heating of the chilled water, and also higher flow rates will cause pumping power unnecessarily high to the power 3. So therefore, it is very important to do the sizing properly, and to make sure that if the flow variation is needed, should be manipulated properly to get the advantage of the power. Yeah. So the capacity can be adjusted by trimming the impeller, which is the simplest but not the best method, by using the variable speed drive. So variable speed drive is an expensive element. So, for example, if you want to change the flow rate from 1 to 2, let's reduce the flow rate from 1 to 2. One will operate at this one particular speed N1, and 1 to 2 can be changed by closing the valve and operate on the same curve and go to 0.3. But you can also do is that you can change the speed of the pump to another speed N2, which is less than N1, and then automatically on the same flow conditions, your flow rate will be reduced. So by doing that, you can save this amount of energy. If not, you had used the valve to reduce the flow rate, this amount of energy will be lost. So that's the basis behind the variable speed drive for changing the flow rate. Because when you change the load, you need to change the flow rate of chilled water, and also sometimes condenser water as well. So this will indicate how the power input change depending on if you are using a variable speed drive or if you are using the discharge valve closing. So you will see that variation of power drop from here to lower value will be much higher in variable speed drive rather than outlet damper the discharge valve control. This will be on motors. You need to select between the standard motor and the premium motor depending on the load. I'm not going into detail. Try to take another 5 minutes to accommodate your questions. Cooling towers, instead of cooling towers operating at constant speed, you can, depending on the load variation, cooling towers can be accommodated with VSDs, right? Same with the air handling unit. To change the flow rate of the air handling unit, you can have the VSD based on the load, and also have the energy recovery unit because the air handling unit will have return air coming from the space, which is cold air that can be recovered. That coldness can be recovered to the incoming air through a suitable heat recovery system. We have different mechanisms by a thermal wheel, by heat exchanger, run around coils, etc. Rather than sending the cold used air directly to the atmosphere, make use of that some heat recovery method to convert part of that or transfer part of that coldness into the incoming air, thereby improving the energy performance of the air conditioning system. I have discussed, this is a kind of VSD that can be used in the air handling unit, the cooling coil, and also incorporating the variable air volume systems, as I showed in the beginning, and using static pressure sensor to control the VSD of the supply fan of the air handling unit. So just note that speed variation to the power 3 is the power consumed by the the blower or a fan, which small variation can reduce the power by a large amount. Same thing, this is incorporating the entire system with VSDs. So you can have a VSD in your air handling unit. You can have VSD in your chill water pump system, that the water that goes to the chiller. And you can also have VSD in the cooling tower and the condenser water system. So, of course, most important would be here, there, and the last would be the condenser. It's quite rarely used in this. Of course, if there is, it's a case of decision will come on the economic reasons. Then incorporating the building automation system to control your end-use devices using PLCs, and well, this shows how the VAV units, lighting, the boilers, etc., can be controlled at two-level central control, and they can also be connected to the internet and converted into a smart control system. Operational strategies. So here, condenser water supply temperature and the chill water temperature. Here, this graph will indicate how COP changes can take place by changing the chill water leaving temperature and the reduction in condenser water temperature for different chiller types, screw chiller, centrifugal chiller, etc. For example, if you take leaving chill water temperature by changing from 6 to 7 degrees, changing by 1 degree. For a screw chiller, you can change the COP by this amount.
Sanjay, have you lost Professor? I think he's experiencing some power cuts, isn't it?
Yeah, Ms. Ryan, I think there is some network issue. We'll wait. I think at the beginning, Professor said that he will join within.
Yes, yes. Okay, ladies and gentlemen, then your attendance Google form is in the chat box. It's in the Zoom as well as in the YouTube channel, and you can mark your attendance. And if you have any question, please put into a WhatsApp group. And Sanjay, can we activate the chat box as well? Because now it's now 8.
Yeah, it is activated now.
Okay, the chat box is activated, and you can drop your messages, especially the questions only, put into the chat box. And if you need to ask it directly from Professor Pathalage, you can raise your hands, and we'll give the opportunity on first in, first serve basis. You can keep your hand raised, and we'll give the opportunity. And please rename yourself, like the people like I can see a hand raised like RD iPhone X is something. Please rename yourself. And please don't put thank you messages. Please don't put thank you messages in the chat box, because it could be interrupting to others. Please don't put thanks messages. We highly appreciate your generous thanking messages, and please don't put into the chat box, because it could be highly interrupting to others, because there are questions to come in, and we let the questions to put in the chat box only. And please put your questions only in the chat box so that we can get it from Professor being answered. At the same time, you can keep on your hand raised, and if we run out with the time and the Professor is experiencing some power failures, and if you have further questions, you can simply put them into the chat box, or else you can compile them and send us a WhatsApp message to myself or Kumar or organizing committee.
Narine, sorry for disturbing. Mr. Kapila, can you make Professor Rahul as co-host?
Professor Athalage is in right now.
Yeah, can you hear me? Yeah.
Yes, sir. Yes.
Yes. Yeah, there was a power interruption. Yeah.
Yes.
You need to. Can I share the?
Yes, yes. Please. Sanjay, shall we make Professor as a co-host?
since the interest of the time, I think probably what I would suggest, I take the questions with
Yes,
slides
Professor,
will be,
there are 2-3 hand raised. Shall we go with this hand
yeah,
raise?
yes.
Yes. Okay. I can see somebody of RD iPhone. Please rename yourself, and I can go to the next participant, Stephanie. Please unmute yourself and raise your question. Stephanie, or else Dilrukshi Prasangika. You have a hand raised. You can either ask your question in English or in Sinhalese, no worries. On a language you can handle tamangite prashne. Dilrukshi.
Hello.
Yeah.
Yes, please go.
මට දැනගන්න ඕනේ මේ දැන් chiller plant දෙකක් තියෙනවා නම් අපිට ඒක interconnect කරගන්න පුළුවන් නේ. එතකොට
Chillers තියෙනවා.
chiller plants දෙකක්.
Okay.
එතකොට මේ ඒක දැන් මට උදාහරණයක් විදිහට chiller plant 1 and 2 කියලා ගත්තොත් එකේ chiller plant 1 වල ඉඳලා 2 වලට interconnect කරගන්න පුළුවන්. එතකොට chiller plant 2 වල ඉඳලා chiller plant 1 වලට ඒ line එකම ගන්නවා නම් chillෝට මේ supply line එකයි chillෝ return line එකයි change වුණාට කමක් නැද්ද? ඒ කියන්නේ මේ දැන් chiller plant 1 වල ඉඳලා chiller plant 2 වලට යනකොට supply line එක තියෙන එකම අනිත් පැත්තට යනකොට return line එක උනාට ප්‍රශ්නයක් තියෙනවද? එහෙම මොන හරි standard එකක් තියෙනවද කියන එක.
මට question එක හරියටම plant එකක් කියන එකේ මට හරියටම තේරුන්නේ නැහැ. මොකද කියන්නේ ඒ කියන්නේ common header එකක් common header එකක් තියෙනවා.
ඔව් common header එකක් තියෙන එක.
ඔව් common header එකක් තියෙනවා separately return එකටත් ඒ විදිහටම තියෙන්න ඕනේ. නැත්නම් ඔව් අතරමඟ ඉතින් මේවයි ඒ දෙක කනෙක්ට් කරන ලයින් එකක් තියෙන්න පුළුවන්. ඒකෙන් ඉන්ටර්මීඩියට් කන්ට්‍රෝල් එකක් තියෙන්න ඕනේ. Tamanට ඕන බයිපාස් කරලා නැත්නම් මික්ස් කරගන්න පුළුවන් විදිහට. මම හිතන්නේ ඒක දන්නේ ආන්නේ කියලා. නැත්නම් normally independently යන්න පුළුවන් විදිහට තියෙන්න ඕනේ. දෙක කලවම් වෙන්න විදියක් නැහැ. මොකද නැත්නම් එක plant එකක තියෙන එයා කේට කරන load එක අනුව තමයි return line එක එන්නේ. supply line. ඒතකොට common header දෙකක් තියෙනවා. ඒ කියන්නේ නිකන් primary circuit එකකුයි secondary circuit එක තියෙනවා වගේ. ඒතර තියෙනවා ඒ දෙක couple වෙන circuit එකක් තියෙනවා මැද connect වෙන. ඒක interconnect කරන value එකකින් control කරන්න තියෙන්නේ. ඒ වගේ condition එක යනවා මිසක් නැත්තම් return එකයි supply එකයි plant එකේ වෙන වෙනම මාරු කරගන්න විදියක් නැහැ. මොකද දෙකේ load එක වෙනස් වෙනද එහෙම කෙරුවොත් chill water ඒ කියන්නේ circuit එකට effect වෙනවා. මම හිතන්නේ ඒක වෙන්න ජහන නැති කියලා.
ඔව් අර ඒ කියන්නේ මේ මට දැන් දැනගන්න ඕනේ අර එක line එක කියන්නේ මේ දැන් එක වෙලාවකදී chillවට supply යන line එක මේ ඊළඟ දැන් අනිත් plant එක connect වුණාම මේක chillවට return එකක් වෙනවනේ. මම කියන්නේ bypass line එකකින් connect කරොත්.
ඔව්.
එතකොට ඒක අර මොන හරි ස්ටෑන්ඩඩ් එකක් තියනවාද එහෙම මේ ලයින් එක මේ chillවට supply යන්න ඕනේ එහෙම කියලා.
ඔව් normally the design condition එකේ දෙක separately independent header එකකින් තමයි යන්න ඕනේ. ඉතින් අර නැත්තම් physically mix වුණාන් පස්සේ අනිත් plant එකේ return line එකේ එන condition එක මේකට බලපෑමක් ඇති වෙනවා නේ. ඒකයි. Yeah.
Okay, Arul, thank you.
Okay.
Aruliti Kantuvel. We can see a hand raise. Nadisha Gamugi.
Sir,
Nadisha Gamugi, please. Yeah, please.
සමහර දැනගන්න ඕනේ අපේ ගොඩක් ලයින්ස් වල සර් අපිට ෆ්‍රෙෂ් එයා ඕන කරන වෙලාවකට ෆ්‍රෙෂ් එයා එක සර් දෙද්දි ඒකේ ඇම්බියන්ට් ටෙම්පරේචර් එකත් එක්ක ෆ්‍රෙෂ් එයා එක එන හින්දා ඒක කූල් කරන්නත් වෙනම අපිට මේ AC ලෝඩ් එකෙන්ම යම් ප්‍රමාණයක් යන හින්දා අපිට සර් ඒකේ ඒ කියන්නේ අර මේ ෆ්‍රෙෂ් එයා සිස්ටම් එක සම්බන්ධව මොනවද ගන්න පුළුවන් හොඳම ඩිසිෂන්ස් දැන් සාමාන්‍යයෙන් අපි සමහරලාට බිල්ඩින් වල පසුවට තමයි ෆ්‍රෙෂ් එයා එක අපිට ඕනේ කියලා කියන්නේ මේ සමහර ඔය දැන් අපි ටෙනන්ට්ස් හය කරන තැනක වගේ නම් මේ බිග් ස්පේසස් ඒතර ඒ කට්ටිය පස්සේ රික්වයර්මන්ට්ස් එනවා මේ ෆ්‍රෙෂ් එයා ඉන්ලට් ඕනේ අපිට මෙහෙමයි කියලා. එතකොට ඒ වගේ වෙලාවකට අපේ චිලර් සිස්ටම් එකත් එක්ක අපිට මොන වගේ කම්බිනේෂන් එකක් දෙන්න පුළුවන්ද එෆිෂියන්සි එක වැඩි කරගන්න.
ඒ කියන්නේ ඩිසයින් ස්ටේජ් එකේදී දන්නේ නැහැ
ඔව් සර්.
fresh air requirement එක එන්නේ aspect 62.1 එකේ හැටියට fresh air requirement එක තියෙනවා occupancy level එක අනුව. හරි. ඒ කියන්නේ per person තියෙන carbon dioxide emission එක release කරන්න පුළුවන් විදිහට fresh air requirement එකක් එනවා ඒ supply මොකද්ද channel එකට. හරි. එතකොට අපි පස්සේ වැඩි වුණොත් fresh air මොකද fresh air එන්න ඕනේ supply air cooling මේක හරහා වෙන්නේ මොකද ඒක dehumidify වෙන්න ඕනේ. dehumidify වෙලා supply temperature and RH එකට match වෙන විදිහ තමයි මේ RH උත් control කරන්න ඕන. නැත්නම් supply temperature එක judge වෙන්නේ ඒ cooling coil එක හරහා එන air flow rate එකට. හරි. එතකොට ඒක හරහා එන්නේ නැතුව වෙනම දැම්මොත් additionally humidity එනවා. එතකොට ඒවන dedicated තියෙන්න ඕනේ වෙනම pressure line එකක් එනවා නම් Taman design එක කරපු නැති එකක් ගේනවා නම් ඒක වෙනම pressure cool කරලා dehumidify කරලා තමයි මේ ඇතුළට ගේන්න වෙන්නේ. හරි. ඒක දහන්නේ
මම හිතන්නේ බලාපොරොත්තු වෙන්නේ මෙයා ඒ වගේ දෙයකට මොකද කරන්න පුළුවන් කියලා. කියන්නේ pressure requirement එක කොහොමද අපිට match කරන්න වෙනවනේ. කියන්නේ air quality
එතකොට initial system එකේ ඒ pressure එක additional එක කරගන්නේ damping requirement වලින් එහෙම කරගන්න බැරි නම් වෙනම additional line එකක් ගේන්න වෙනවා. ඒ additional line එතකොට dedicated pressure වල dehumidify කරන්න වෙනම cooling unit එකක් දාන්න වෙනවා. සාමාන්‍යයෙන් additional එකක් දානවා නම් normal design එකට අමතරව fresh air විතරක් add කරලා හරියන්නේ නැහැ. මොකද fresh air විතරක් add කරනවා කියන්නේ humidity load ලේකුත් ඇතුළට ගේනවා කියන එක. එහෙනම් ඒකත් අර වගේම dehumidify කරලා ගන්න පුළුවන් එකක් තියෙන්න ඕනේ. දැන් lead certification වල මේක සාමාන්‍ය පාවිච්චි කරන. ඒගොල්ලෝ කියනවා additional එකක් එනවනම් ඒකට marks තියෙනවා. ඒ ඕනනම් ඉතින් fresh air එක additionally දාන්න පුළුවන්. එතකොට ඇතුළේ තියෙන humidity controlling වලට ප්‍රශ්නයක් වෙනවා. ඒකින්ද ඒකත් dehumidify කරලා අවශ්‍ය කරන condition එකක් හැටියට තමයි additional කියන්නේ. වෙනම unit එකක් එකට ඕන වෙනවා. එහෙම.
සර් ඒකේ මේ තව පොඩි ඇඩිෂන් මේ කරුණක් විදිහට අපිට fresh air එකේ cooling එක ambient එකට අඩු කරන්න අපිට condenser line පැත්තෙන් හරි අර heat transfer එකක් කරොත් එහෙම ඒක
අර කිව්වා වගේ අපි දැන් හිතමු දැන් use කරපු air එළියට යනකොට exhaust air හැටියට okay එක්තරා දුරට contaminate temperature එක අපි එළියෙන් එන air වලට වඩා අනිවාර්යයෙන්ම අඩුවෙන් තියෙන්න පුළුවන්. එතකොට ඒක පාවිච්චි කරන්න පුළුවන් heat transfer එකක් හැටියට ඒ කියන්නේ supply එක පොඩ්ඩක් pre cool කරන්න. ඒ කියන්නේ exhaust අපි එළියට යන එක heat recovery system එකකින් ඒ coldness එක supply එකකට පාවිච්චි කරන්න පුළුවන්. ඉතින් ඒ වගේ unit එකක් පාවිච්චි කරන්න පුළුවන් pressure එන ප්‍රමාණය කීයද කියලා හරියටම දන්නවනම් ඒ වගේ matching එකකින් පුළුවන් ඒ incoming additional pressure එක dehumidify කරලා ඇතුළට ගෙන්න ගන්න supply එකත් එක්ක ගන්න.
පැහැදිලි sir. හරි thank you sir.
Thank you. We have engineer Joga Praja.
Hello sir.
Yes, please go ahead with your question.
Sir, my question is there is a old building about 20 years before constructed. It has some old static system, sir. Is it possible to convert some by adding some parts and convert it to variable system, sir?
You mean to say VRF systems?
Yeah, VRF, sir.
Well, VRF system, yeah, can be incorporated. Okay, if it is a chiller system, there are many places where you can incorporate the VRF. So let's say it can be to the chiller itself, or it can come to the well. If you have AHU, you can also have the AHU supply fan converted into the variable VSD variable speed drive. Then you can also have VAV boxes installed into the zone level. If there's a return fan, that can also be incorporated. Yeah, generally, depending on your, cost availability, you can you can decide on the evaluation of the benefits that bring into the system. and you can incorporate the VSDs into different points, starting from the lowest, from the fans to the pumps, and then to the even to the chiller. So in that case, chiller, of course, then you need complete replacement. But if not, the smaller units like HU fans, the circulator pumps, etc., VFD can be incorporated. So that's quite normal.
So I think he must have meant like the VRV systems. I think instead of static chiller system, just to convert into VRV. I think there should be a lot of physical modifications, like especially outdoor
variable refrigerant volume, not not VRF. Yeah.
Yes.
Okay. Okay. Not VSD. VRV.
No, VRV.
Yeah, of course that's possible. But requirement is that whether it's VSD or VRV, the requirement should be if there's going to be a real load variation, right? If there is no load variation, even VSD is not going to be useful. I mean, from a principal point of view, VSD, if there's a load variation only, that will bring benefits for the additional investment that you are going to make. If not, that's not going to be, because it's VSD, that's not going to bring benefit. Same with VRV. If there is no, I mean, in the installation, there is no real variation in end use, let's say like a school or something, where one class is going to be differently loaded, then it makes sense. But if it's like an office where the loads are well known and it's constant throughout, and it starts at a particular time and it's over at a particular, then changing a system completely into a VRV will not make sense unless it has a real variation that can be justified. The benefits can be justified by the additional investment.
All right. Okay. Thank you. Thanks.
True for VRV or VSD. It's the same principle.
Right. Thank you. Thank you very much. And I think we are done with the questions. And if any of you have any further questions, please put into our WhatsApp group, and then we'll discuss with the professor. Professor, thank you very much. And Professor, do you have anything to mention something for the final remark? Because especially for this, there are a lot of undergraduate students here.
Right.
And the value of this CPD programs and the future trends. Like we have a lot of challenges, obviously, in the future. So how we can be prepared for those?
Yeah. Final remark is that some of the slides that I had planned in the remaining, which I could not, my focus was to make them aware that the three elements that which I highlighted: the energy performance, indoor air quality, and the thermal comfort. These are the three pillars in any air conditioning design. All this information have to fall in line with the typical ASHRAE standard. That's energy performance should be with 90.1, and thermal comfort should be ASHRAE 55, and indoor air quality is 62.1. And so my advice is that any person who is planning to embark or develop the career in this area have to be thorough with this use of these standards, because standards is the one that brings all the past information and experience of engineers into the current context. And if any design is in line with this ASHRAE standards, will be a real benefit to bring the past experience into the current context. And therefore, a lot of effort, development and capacity building would be needed in knowing the ASHRAE standard, definitely, which will be coupled with the building simulations. And there is some level of mastery using a building simulation tool would be needed, like eQuest or Enervin, and there are a few others. eQuest is a good candidate because it's public domain, it's free, and it can be learned easily. So standards with the building simulation will be a good combination for an undergraduate to embark as a professional in the building services engineering sector. So that's probably the message that I would give for the class candidate.
Thank you very much, and
Yeah.
thanks a lot, especially on a Sunday evening, that spending time with. There were a lot of participants, and we have recorded in the YouTube as well. We will share with everybody. And
Right.
again, thank you very much.
I hope I will send the slides in PDF format. You can distribute so that anybody who
Appreciate.
would, I mean, the slides that I could not cover can be. So there are 1 or 2 examples at the end, which might be useful in completing the module.
Highly appreciate, sir, because I felt a little bit guilty to request from you, but there were a lot of requests through chat books and even through WhatsApp groups and how we can get the slides. So
No problem at all. Yeah,
thank you.
absolutely.
Thank you very much, and highly appreciate, sir.
Yeah.
And again, ladies and gentlemen, thank you very much for staying with us until 9:30 right now. And anybody who is marking your attendance, you can right now mark the attendance. And especially if you have any, like if you couldn't mark your attendance due to power failures or signal failures, what we recommend is to keep at least 2-3 screenshots to prove your attendance. ඔයාලට කොයි වෙලක හරි attendance mark කරගන්න බැරි වුණා නම් power failure එකක් හරි signal drop එකක් හරි වෙලා තිබ්බනම් අපි recommend කරන්නේ YouTube එකේ බලපු එකේ screenshots කීපයක් හරි තියාගන්න. සහ එහෙම බැරි වුණොත් පසුව හරි මේක YouTube එකේ බලලා අපිට විනාඩි 30 slots වලින් screenshots එකතු කරලා අපිට දෙන්න. ඒතකොට අපි ඒක සාධාරණ demand එකකට අපි සලකනවා. ඒක attendance සඳහා අපිට බලාපොරොත්තු වෙන්න පුළුවන් අපේ සංවිධායක මණ්ඩලයට. With that remark, ladies and gentlemen, thank you very much. You have been a great audience throughout this last 2 hours, and especially again, thank you very much, Professor, spending time with us and sharing your wealth of knowledge among this, especially the audience who was seeking eagerly. And it was a pleasure to having you as a first presenter today. And thank you very much, ladies and gentlemen. Have a pleasant evening. Good night.
Yeah, my pleasure. Thank you for inviting me. Right. Thank you. Right.
Thank you, sir. Thank you.
Good night, everybody. Yes.
Good night. Sanjay, shall we conclude the session, please?
Sure, Mr.